And in this part, we will focus on WAL and trigger-based replication. For WAL-based replication, which refers to write-ahead lock, we will not only cover replication with it, but we also dive a bit deeper to see why we need write-ahead locks and how it works on example of Postgres database. So let's start with the replication based on write-ahead logging. Almost all databases, in order to achieve durability, they use so-called write-ahead logging. Basically, before any change is applied to the data itself, a log record is written about what exactly is going to be changed. And then this is changed. This is needed to achieve durability, so if a database server fails before applying write, it could restore it from the log. But let's see how it relates to replication. The idea is that write-ahead logs, they are very low level, and because of this, they are very effective. Naturally, the idea comes to mind to just use this log, which we anyway write, to replication. So we already have log, we could just take it from leader, transfer it to follower and reapply. Why do we need separate log for replication and separate for durability protection? We could just reuse the same log. And the image on the screen conveys the main idea of it. So as usual, we have our booking system for meetings. Bob creates a meeting and adds two participants. It's using SQL. And but now it's interesting to see what exactly is transferred between leader and follower. In Postgres, for example, the unit of change in write-ahead log is called XLog record. So basically we have 4 XLog records, one for each statement. And as you can see, it's not full content of that record, it's just some example of most important information which is present in those records, just to give you idea of how low level it is. For example, this XLog records has some flags, has type insert, then it provides some reference to which node we are updating, which exact block on the disk of this node we are working with, what is offset, the tuple date. The tuple is just basically a row in the database. Also, it has some information about transaction and this ID of this log record. So basically, as you see, comparing to, for example, row-based replication, where basically we just had this tuple data. Now we have a lot more information which say how exactly it's stored physically. This replication method is used in 3 databases. It's Postgres, Oracle, and IBM DB2 in HADR mode. It has several benefits, and the main benefit comes from the fact that it's a low level and effective log, and because of this it's very fast. And also we don't need to create any other separate kind of log because we can just reuse one. The second benefit is that non-determinism is not a problem because we just basically say which values are changed, not the comments. But unlike row-based replication, we don't just say that some values were changed, but we also say how to apply those changes and what data blocks needs to be changed. And the third benefit is that since it's kind of low level and physical, it does not focus only on row changes. We could use the same method for transferring any changes in the database. For example, DDL changes, not a problem. We created a table, okay, it also generates write-ahead log and we can just transfer it. But there is a kind of major drawback because of those very low-level XLog records. They depend very much on the exact version of the server, and it complicates upgrades a lot. For example, if we have a system which must work 100% of the time, we can't just stop at update leader and all followers and then bring it back. And if we update leader, for example, then those low-level changes, low-level interface, it might become incompatible between each other, and upgrades in such systems are real pain. So, because this write-ahead logging it's very tightly linked to the database internal structure itself, in order to understand this replication technique better, we need to just make some deeper dive into how it works. Just to be specific, I'll be showing examples on how it works in Postgres SQL, but in general of those concepts and ideas, they could be extended to almost any databases. First, we need to understand that usually databases, they store data on the disk. So it's depicted here, and on the disk there are files. So in databases, those are called data files, and in those files, database processes store data. Each file is split on multiple pages of fixed size, and when some data is written, a new page is created in this file, and once all file is occupied with data, and there are no more free pages available there, another data file is created by Postgres, and pages are written into that file. Page consists of multiple tuples. Tuple is just a row in a relational database or a document in document-oriented database. It's just for historical reasons. Those things, they are called tuples in the databases internally in their implementation. In the source code, for example, in some internal low-level documentation. It's important to note that even if we want to update one tuple, one row, we have to update the whole page, because in Postgres, page is minimal unit of change. So basically, if we want to change some even small piece of data, we need to load page into the memory, update it, and store it back on the disk. On the first glance, it might seem to be ineffective, because why, in order to make write of some small piece of data, we need to update the whole big page? But the reasons are that underlying storage usually supports only block granular writes. So usually on disks, we can't just update specific bits of data. We also have some blocks, and we have to update the whole block. So database servers, they just have to work on what they have as a physical storage and have to adapt to it. Because of it, they also need to make this kind of paging and writing and reading the whole page. And also, as you know, with disks, there are two types of access. Random access, when we just want to access a data in some random part of the disk, here, for example. And there is sequential access, and sequential access when we read or write data sequentially, how they are located physically on the disk. For example, it can go like that, row by row. And it's known that random access is much slower than sequential access. Because of what we said, it's obvious that in such database, if each comment which changes the data would have to update the whole page, and also since we could update arbitrary piece of data, it could be located in any page, so it means that we would have to make random access write of a relatively big page on each hour write. It's obvious that such system would work very slowly. So we here come to the solution with caching. In this solution, we have shared pool which contains pages. Those pages are called dirty pages if they have some changes which are not yet written on the disk. And then when write comes, it updates just page in memory, which is very fast. And then we have some regular checkpoint process which just gets dirty pages from the shared pool from memory and writes them to the disk. And it works much faster because when we write, we just have to update memory. And for example, we might have done thousands of writes, and all of those writes, they were applied to only 3 pages because we just updated data in such a way that we accidentally updated them on some limited amount of pages. And we just need, in checkpoint process, we just need to make writes of 3 pages instead of 100 writes. So it works much faster, but it introduces problem with durability. Indeed, what would happen, for example, if client send a write, it was written to memory, checkpoint process yet haven't stored it on the disk, and the server crashed. It will mean that data which were recently written and not yet were written on the disk, they will be lost forever. Obviously, it's not good, and this drawback by itself would not let us use such system even it's fast. It's fast, but it does not guarantee anything. So what's the point in such a system? And here we come to the idea of write-ahead logging. So basically, the idea now that each change is written into the shared pool, the page is updated, and also we have this write-ahead log buffer in the memory, which contains XLog records for every change. Now, for each change, we need to make several things. First, we update page in shared pool. Also, we create XLog record for each change, and we add some incremental information on what exactly was changed in which page. And then, when transaction is being committed, this WAL buffer is being flushed to the disk. But shared pool is not flushed on the disk. So basically, now on each write, we have to write to the disk this part, which is related to WAL, but not this part. And this part is still being flushed asynchronously with checkpoint process. This solves problem with durability for us, because write-ahead log, those WAL segments, they will contain all changes. And now, if server crashed, we anyway have all changes for committed transaction recorded on the disk. And when Postgres starts, it could discover that it has some changes which were not yet applied to the disk, and it can just reapply them, and thus data will not be lost. One can ask a question. So if we anyway on each commit, we need to write something on the disk. So basically, instead of writing pages, we write XLog records. Would not that be slow, and would not we just throw away all benefits which we introduced by adding those shared pools memory buffers? And the answer is no, because first of all, remember what we said about random access and sequential access, that random access is slow and sequential access is much faster. And XLog records, they are written sequentially. So because of this is fast. And second reason, that XLog records, they are much smaller than pages. One XLog record, it contains only small diff of what exactly was changed. It does not contain the whole page. And all of this makes flushing of WAL records on the disk much faster process. And here we have a solution which combines durability and also speed of executing transactions and writes. Having looked at this, let's dive deeper and see internal structure of the page and the XLog record. So let's just scroll to this section, and here we just zoom to see what is the page and what is the WAL segment. So page, it contains some header, it contains some tuples, which are basically rows data in Postgres. And in the middle, page has a free space named whole. Basically, the idea is that page has fixed size, and the tuples, they can have variable size. So in order to quickly find a needed tuple, we need some way to point to them. Because of this, in the header portion, in the beginning of the page, we have those tuple pointers which have fixed size, and we can always very quickly find the needed tuple, and in that tuple we could find a pointer to the page. And here it's our XLog record. It has some kind of header part which is called XLog record itself. It has a data part which is also have some header and data, and the data correspond to the tuple itself or rows, some specific attributes which we store in each row. And each XLog record, it has its unique ID, which is called LSN, log sequence number, and each page has corresponding this PD LSN, which links it to last XLog record which changed this page. And just to understand what's inside of this XLog record, let's see this source taken from Postgres SQL sources. The link is given here. So we see that those XLog records, they are very low level. So for example, they contain some flag bits, they contain resource manager for this record. So the idea here that different changes to the database, they are encoded and decoded by different resource managers. And in order to say which resource managers need to decode this specific XLog record, we need to provide its ID. And remember that we are going to use this write ahead log to transfer it from leader to follower and apply on follower. And it's easy to imagine that when Postgres evolves and there are new versions, there could be additional resource managers, or resource managers could be changed, for example, and they could process the records differently. And because of all of those low-level details, we can see why there is a problem of making updates of such system. Because if we change leader but not change follower, it's very, very likely that something of those low-level parameters, they will not fit together and something will be broken. I have provided this data not to have deep discussion about internal implementation. I just want to show some minimal amount of data to explain the root cause of the problem and why it's difficult. Now we have some conceptual understanding and idea on how write-ahead logs work in Postgres internally, and it will be very easy to understand how they are used for replication. So in Postgres terms, when we say about leaders and followers, we just name them primary and standby. And initially, here we have primary and standby servers. And we have these XLog records with LSNs which are available in those logs. Remember that LSN is log sequence number. It's just some sequential number which is assigned to each XLog record. And we see that initially leader has last LSN is 100 and follower has LSN only 80. It means that it's behind by 20 XLog records. When standby starts, it has two processes, WAL receiver and startup. And startup, it understands that Postgres is in standby mode, and it starts WAL receiver process, which sends connection request to primary server. It just acknowledges it and then transfers TCP connection to WAL sender process, which it creates for this standby. And then primary and standby, they begin negotiation, and standby sends most recent LSN, which is available in its database, and WAL sender process, it just sends all the changes since that last available record. So in our case, it means that it has to send XLog records starting from 81 to 100. And when this process is completed, now their logs are synchronized. So follower has all 100 records in its internal storage. And now we have streaming replication when WAL sender just sends XLog records to standby as soon as they are created on its side. And standby, once it received those records, it just applies them on its local database, and thus state of primary and state of standby, they are just synchronized. And the last replication method, which we will cover today, is trigger-based replication. It's very different from all previous replication methods which we discussed so far, because before that, this replication was kind of built into the database. And the trigger-based replication, it's usually something external to the database, which sends changes to another database. The idea is that usually databases have triggers. Triggers is just some pieces of code which could be executed when some event happened in the database. For example, when some record was updated, when a record was inserted, deleted, it can cause firing trigger. And this trigger can have a stored procedure which can basically execute any logic. And those triggers are internal database functionality. And we just can use them. We can write custom triggers which would catch all changes to the data, and they could trigger transfer of this data to some external sources. For example, let's see how it works. On this picture, we again have our booking system, and Bob creates 2 meetings and then updates them. Now we have our table, and we have trigger on the leader which listens insert, update or delete events. And what this trigger does, it just stores them in the special table named changes. And here it stores in what table the change happened, what operation was there, for example, delete, update, insert, and what exact data were changed, which is basically all columns of the row. And there is some external third-party replication process. We could use our own process, or we could use some framework which does it. And this replication process, it just constantly listens to the changes table and applies them to follower. So those records which are being sent, they could look like this. It's just a record of those changes table. So there is table name, operation, primary key, it identifies which row was changed, and the row data. And thus, for each change, we have separate message which is sent to the follower and applied on it. This method has some properties which usually other replication methods doesn't have, and main benefit is flexibility. Because with triggers, we could replicate not the whole database state, but for example, we are interested only in some specific table, and we could just set up a trigger only for this table and replicate data only for this table. We can go even further, and for example, we could replicate just specific rows of the table. For example, there is a big table, but we are interested only in some portion of it, and we can replicate only it. We can also apply any transformation in the replication process, because we have a freedom to change this replication process and transform our changes. Apart from that, we don't have to send those changes only to follower. We could send them to some other system. We could send them, for example, to our Kafka or other message broker to just reuse them in some other way. Also, what is really good about this approach, we don't have to use the same database. For example, we could have Postgres here, but we could have MongoDB here, because it's just we need to map the relational structure of the Postgres to document structure to MongoDB. And it all can be done in our replication process. So basically, it's very, very flexible. But unfortunately, despite of all those benefits, we still have drawbacks here. And the first major drawback is that this trigger-based replication, it's not something native to the database. It means we need to have some complexity, to have some external application which kind of being part of our replication stream. And because of this, it does not work as effectively as the database native replication, because it's something on top of the database. So it's complex, so there is overhead related to the complexity, and also there is a performance impact. And there is one other problem is that triggers, they could be buggy, and this could lead to drift between states of leader and followers. So usually this method, in general, it's not a default choice probably, but it's a very useful option when you need something special, when you need a lot of flexibility of what to do with your data. In theory, you could implement it fully yourself. Database provides triggers, you can have any logic inside of them, you can have external application which can contain fully custom code. But there are other options, and there are some frameworks which allow to automate this trigger creation, this replication process. So if you want to use trigger-based replication, you might want to check those projects. First three of them are for Postgres SQL, and there is a symmetric DS, which is interesting because it supports multiple databases and it allows cross-database replication, where you will need to write minimum amount of code and most of boilerplate things which will be handled by the framework. As a summary, I'd like to compare those methods and highlight their differences, benefits and drawbacks. First, let's review what exactly is being replicated in each method. So in statement-based replication, it follows from its names, statements itself are replicated. So basically insert, update, delete. In row-based replication, we just send changed rows, not statements. With write-ahead log replication, the low-level write-ahead log records are being sent over the network. And in trigger-based replication, we again send changed rows, basically, but we can transform them in any way we want. Statement-based replication, it has very compact log, which can be used as audit for free, we already have it. And there are no strict requirements for matching versions between leader and follower. And it can be used for both DML and DDL statements. The benefits of row-based replication is that it doesn't have any issues related to non-deterministic statements, and still it doesn't have strict requirements between matching versions of leader and the followers. And also it can be used in more extended sense as a CDC, change data capture, to transfer a stream of data to our custom applications, not to the databases itself. WAL-based replication also does not have any issues with non-determinism, and it's extremely fast and effective because it's being very low level. And also it can be used for both DML and DDL statements. And main benefits of trigger-based replication is that it's database agnostic and very flexible. Now let's look at the issues. Main issue of statement-based replication is non-deterministic statements like random, null, lux, and so on. Issues of logical replication is that it's very verbose in case of bulk operation and a lot of data needs to be transferred, and also it focuses on rows, so it can't be used directly for DDL statements which modify table or modify some schema definition and so on. And the main drawback of write-ahead log replication is that it's low level and it usually requires exactness of versions of leader and follower, which complicates upgrades a lot. The drawback of trigger-based replication is maintenance overhead and performance impact, and the risk of drift and complexity of setting up this schema because there are some external components on the top of the databases. And finally, let's review the systems which use one or other replication method. It seems that purely statement-based replication is used only in old versions of MySQL. Role-based replication or logical replication is used in most of the systems, and some systems like Postgres, Oracle, IBM DB2 in HADR mode, they use right-hand log replication. And for trigger-based replication, there are some projects which can support multiple different databases, and they are kind of external tools. And they can be applied, for example, symmetric DS can be applied to any database. Here is the list of references which I reviewed in order to create this video. So if you want any details, you can visit my website, find this article in the text form, and just have some deeper reading on any of those links. I hope you enjoyed this video. In future, I'm planning to make even more deep dive into this topic, and my next videos will be about consistency models and their applications, specifically which can be achieved in leader-follower system. So if you are not yet subscribed, just do it in order not to miss interesting videos. Bye!